The electric motor is one of the cleanest and most useful machines used in society today. It can be found in everything from tape recorders to cars. This session is about the relationship between electricity and magnetism, focusing on the electric motor. The outcomes of this lesson are for learners to understand the motor effect, to perform a simple experiment to demonstrate the motor effect, and to make a simple electric motor. At Fundoguhle Secondary School in KwaZulu-Natal, the teacher is introducing a lesson to demonstrate the motor effect.
Class, our lesson today is an investigation. What we want to find out here is the direction of the force that we get if we have got the magnetic field and the current bearing conductor in that magnetic field.
In order to do the experiment, learners are given a battery pack, leads, a magnet, paper clips, press stick, and a strip of silver foil. Learners are also given a worksheet with instructions on how to connect the equipment.
The first step that we have to do here is to bend the paper clips.
After the teacher demonstrates how to assemble the apparatus, the learners do it for themselves. The two clips are placed onto press stick about 10 centimeters apart, and a strip of silver foil is strung between them.
Connect the positive terminal and the negative terminal with two of your leads. Take your magnet, identify the North Pole and the South Pole. Bring the magnet next to the strip of aluminum foil and identify the direction of the movement of the aluminum foil.
The teacher observes the different groups and offers advice.
Right. It seems like the foil is not moving. Can you suggest the reasons?
I think maybe the strip of the foil is maybe too big, the size is too big or something.
Right, so get the scissors, shape it up to the smaller size. The style of the lesson is mostly self-discovery. I try to hold myself, not to tell the learners the outcome. They must find it out.
To obtain controlled results, the learners draw diagrams showing the direction of the current across the foil, as well as the results when the north pole of the magnet and the south pole of the magnet are brought closer to the silver foil. Learners are expected to experiment on their own and write down their observations as accurately as possible, and then to discuss what they have seen so that they can come up with a rule. This is known as discovery learning.
Traditionally, science was presented as a body of knowledge. I think learners got the idea that it was a fixed body of knowledge, and they were expected simply to master it and accept it as it was presented. With discovery learning, however, they presented with opportunities to discover concepts and ideas. In order to do that, they need to utilize a number of skills, some of them practical, like observation, measurement, and some of them cognitive, because in discovery learning, they have to think about what is actually happening and try and come up with explanations for themselves. And so discovery learning is very suited to outcomes-based education.
This is the positive and this is the negative. Put north, it goes upwards. So then when you change it to put the south, it goes downwards. Means the force goes downwards.
The learners draw the direction of the force on their diagrams, and then the experiment is extended.
Now, you leave your magnet. Change the polarity only. So this side must be positive, the other side must be negative. Again, identify the force.
The teacher emphasizes the need for controlling the variables when doing science experiments.
You check one thing at a time. If you are checking the polarity of the magnet, you do not change the direction of the conventional current. That is very important in science, that you control your variables.
The learners swap the terminals around and again record the direction of the force.
Then now, this is negative and this is positive. And then when we have north, the force is going downwards. This is south, then we put it, it goes upwards.
By changing the terminals around, learners become aware that the force is now in the opposite direction. The teacher summarizes the results on the board.
In which direction will this current conductor move if the north pole of the magnet is coming?
Upwards.
is upwards. All what we have changed now is the polarity of the magnet. So in which direction will this current conductor move?
It will move downwards.
Downwards. Good.
The teacher completes the results for all 4 observations and a clear pattern emerges.
Whenever I've got the North Pole in this direction, the current in this direction, the force was upwards. So now we've got the rule which enable us or which help us to remember what we've got here.
In this lesson, the teacher uses the left-hand motor rule to explain the relationship between the direction of the magnetic field, the current, and the force exerted on the current-carrying conductor. Although the left-hand rule is still perfectly valid, it has been replaced in the curriculum by the right-hand motor rule, which demonstrates the same principle in a different way. If you position the thumb and first 2 fingers of your right hand at right angles to each other, and you point the first finger in the direction of the current and the second finger in the direction of the magnetic field, then your thumb will point in the direction of the force that will be exerted on the current-carrying conductor. After formulating the motor rule in their own words and getting comfortable with it, the learners move on to see how it works in practice.
The same principle is being used when we want to make electrical motors. Can you mention for me anything that you know that have got a motor inside?
Hair dry.
What motion is being formed there?
They spin.
So now, our lesson now is about making those motors.
Learners are supplied with a battery pack, a roll of insulated copper wire, leads, press stick, paper clips, and a magnet.
So you take your cookie pen and the piece of insulated copper wire.
In this activity, the learners are building an electric motor. It is not a traditional form of motor as it does not have a split-ring commutator. However, it works well and is easy to make.
Understanding how a motor works is important, but learning it simply from looking at a piece of paper is not really going to encourage the kind of learning that making it physically does. When you actually have to put the pieces together, you get a far better understanding of what is actually going on and a better understanding probably about the nature of science and how we use it.
After rolling the insulated copper wire into a coil, the insulation is removed off only one side of the wire at each end. The wire is then placed onto the 2 paper clips in the same way as the previous experiment. The coil is tested for mobility. A magnet is then brought closer to the coil and creates a motor effect.
People learn in different ways, and by getting people to actually construct things, you are probably meeting the needs of a wider range of learners. There's also an element of enjoyment, of course.
When you've got your motor spinning, change the polarity of your magnet and check the direction of rotation.
Learners change the polarity of the magnets and observe the outcomes.
What do you notice about the direction of the spin now? Is it on the same direction?
No.
It changes. If it was moving clockwise, it will move anti-clockwise. Right. You must be able to work that out.
After checking the direction, the teacher asks learners to swap the terminals around and to predict the direction of spin.
Firstly, they have to predict it, to do what we call the hypothesis, to think, I think this is what is going to happen. And then you check it with the experiments.
What do you think is going to happen when I take this terminal and put it that side, and I take that one and put it this side?
The side of the coil that was moving clockwise will move anti-clockwise.
Right? Let's see that happening. Change the poles.
The terminals are swapped and learners check their predictions.
So was your prediction correct?
Yeah, it was correct.
What do you think is going to happen when we change the magnet?
It will change
To which direction?
to clockwise.
Just change the magnet. Does the spin changes?
Yes, it changes.
Good.
What I would suggest to other teachers is to adopt this method of self-discovery, if they can just take it and use it, because it's helping a lot.
Hello viewers, we have just watched a video on the lesson on electromagnetism. And next to me I have Liz from Wits. Mike from WITS,
Hello.
and Kanye from the Science Education Project.
Hello.
When we think of the lesson that we have observed, the teacher provided the learners with apparatus and the worksheet at the beginning. He guided the learners by following the instructions and then gave them a chance to discover things themselves. Is this a good practice?
At one stage in the video, some of the learners were getting very excited about their motors. And I think that spoke a volume to me because they felt they'd accomplished something.
Yes.
What do you think, Kanye?
I think it takes off the notion that science is difficult. At least they were having fun and it was working more than everything. And the apparatus were quite simple to use.
We know science to be a body of knowledge. And in this case, it need to be explored. And what do you think are the best ways of exploring science?
By doing experiments, links the theory with the practice. Because sometimes learners think what's happening in the classroom doesn't relate to everyday lives. So it was really good to relate it to motors.
What the learners actually do themselves is the stuff that they're most likely to remember. It forms the most vivid impression on their memory. So I think from that point of view, the practical work is and investigative, open investigative work was done here is very, very important.
And Kanye, what do you think is the other value of discovery learning? I mean, you saw the teacher giving the equipment to the learners, and the learners were given a chance to discover things for themselves.
For me, what was good was when you were swapping the polarity, because usually science is just a lot of terminology. And here you've got the magnet with the north and the south, and you've got the current, conventional current with the positive and the negative. So I found it sort of clarifies that mystery a bit, where they have to discover themselves, swap the terminals, look at the direction in which the coil is moving, or cut the length of the aluminium foil they were using, look at the changes. You know, it sort of makes the body of knowledge, which would be otherwise abstract, understandable.
If I can just pick up on one point there, that a very nice feature of the video was the point where the learner had noted that she hadn't seen any movement, and the teacher then said, well, what are you going to do about it? And she actually worked out for herself, well, obviously the foil was too heavy, so obviously cut a little bit off. So that was very, very nice, and I think that shows or demonstrates vividly the importance, the impact of discovery learning. So that little segment just lasted for a few seconds, but was, I think, very, very valuable. And that's the sort of thing that learner will never ever forget.
Yes, it's true.
And as a teacher, you would want to bring the attention of the whole class to this discovery. You know?
And in a way, that will also help and motivate the learner that he has or she has discovered something new for herself.
Yes.
And one of the things that came out was the whole idea of variables, that is, control the variables is important in science lessons. Why do you think it's important to control variables in science lessons? This?
Well, I suppose if you've got two variables both changing at the same time and affecting a third variable, then how can you tell the effect of each individual one? So it was very nice the way the teacher said, just change the direction of the current, keep the magnet the same, and then another time keep the magnet the same, but just change the direction of the current. So there was a good opportunity to indicate to learners what we call fair testing.
And also following the cause and the effect.
Yes.
If they just see the result, they must be able to trace what causes this. Now, if they are changing more than one variable, they won't be able to trace it to the correct source.
That's right.
Do you think there was a value in the teacher in guiding them, giving them instructions what to do and what not to do in order to be able to control the variables?
I think it's important at times for the teacher to give some guidance. There are times where it's appropriate to just let the learners have free rein for a few minutes, let them try this, that, and the other. But there are times where one has to pull things together. And and I think that the teacher acted correctly there in emphasizing the controlling of variables. Otherwise, I think that the learners would have simply come out of that lesson with a state of confusion, and obviously the lesson would then have been counterproductive. So I think that the way he controlled that part of the lesson was very good.
I think too that one needs to know something about the theory before you know what to look for.
Yes.
So one's observations depend on your prior knowledge. So there's a bit of a balance needed between leaving an experiment and investigation open-ended and actually giving some structure to it.
And I think that's why the value of this lesson is that it was well structured, because it gave an opportunity to the learners to actually explore. And after the exploration, then the teacher came out with the theory. And after the theory towards the end, therefore, learners were actually asked to design things like that use the motor effect. So they were given everyday materials to design for themselves. And do you think, therefore, the learners will be in a position to remember such theories and practice in future if the teacher has taken this route?
Far more than using a textbook, I would say.
Yeah.
Yes.
I also think the bonus was that the experiment was a success.
Yes.
Because far often you try it and then things just don't want to work. And then as a teacher, you just don't know what to do.
And also it started off with the easier one when they were doing it started off with the pen and then the wire. And then it moved up to the coil and then the paper clips. So there was also some construction of knowledge from a lower level up to a difficult or a higher level. So that I found that very good as well. So how do you actually bring in the whole idea of everyday experiences? Some teachers prefer to do it before the lesson or at the beginning of the lesson. And if we look at this teacher, he has actually done it at the end of the lesson or towards the end of the lesson. Which one works better?
I don't think one can give a clear-cut answer to that. I think sometimes bringing it in the beginning to immediately indicate the relevance of the lesson can be very important. Otherwise, learners will just see the whole exercise as being too academic, too theoretical. So I think it's appropriate to bring in the relevance as early as possible, and then perhaps remind them of the relevance at the end.
Do the application.
And do the application at the end,
Yes. I think the important thing is that they make the links. I don't think it matters where they make the links, as long as they make those links.
And there are a lot of textbooks that the learners use that have some motor effect, or that are talking about electromagnetism. When do you think the teacher should use such materials, the textbooks and other materials? I mean, it was never used in this particular lesson, but I'm just thinking that the education department actually buy books or textbooks for schools. When do you think those are supposed to be used?
Well, diagrams, firstly, it would be very useful to have the diagrams in one's textbooks. And the learners didn't really have a record of what they'd done in the experiment. So if they'd had a textbook, they would have a record to refer back to afterwards.
Yes. I think the textbook is an obvious supplement to the learning material acquired in the classroom. And I think it's perhaps a pity a lot of teachers don't use the textbook like this now, but it would be, perhaps we should encourage teachers to ask learners to read the textbook material before they come to the classroom, just so they've got an idea of what is going to come next. I know it's not done all that often at the secondary level, and that perhaps is a pity.
And maybe afterwards, after the teacher has done this lesson, ask as an assignment, ask the learners to go and read chapter 1, and then maybe come back the following day and discuss the whole issue of electromagnetism.
I think it's important, yes.
Otherwise, he or she can just pick up a problem that will have the lesson as background knowledge, and then in order to solve the problem, they have to find more information from the textbooks. Because when you say to them, go and read,
they don't read.
No, they won't read. No, I think they must be given a definite exercise to do. perhaps told to find the answer to one or two particular questions. So there must be, again, a task. That's right. The homework needs some structure to it. Otherwise, as Kanye says, it's they won't do it.
Yeah.
And on the video, we also saw some the use of the left hand or the right hand rule, and there seems to be some confusion on this rule. Would you like to comment about it, Mike?
Yes, this is an issue about which there's an enormous amount of confusion, and it isn't helped by the fact that over the years, different textbooks have used different conventions and different meanings to the fingers. Just to put it very briefly, first of all, you've got the complication of whether they use electron flow or conventional current convention.
Yes.
Now, I think that the current curriculum has got it more or less right now, that we are going to stick to the conventional current. But then what happened on this occasion was that the roles played by the thumb, the forefinger, and the second finger. Now, hang on.
You must use the
left-hand rule.
The left-hand rule uses FBI.
Right.
So that's thrust,
field
and current.
Yes.
But if you use the right-hand rule,
then it
changes.
FIB.
Yes.
Okay.
So that would be thrust, current,
and the field.
And field.
Yes.
Yes. So I think the important thing is that teachers don't muddle the two things up together.
You know, I'm involved in teacher training, and the advice I give my trainee teachers is this. I say to them, for goodness sake, don't go into a classroom unless you're absolutely confident that you know what rule you're going to use, what convention you're going to set up, and just stick to it consistently. I think that is absolutely important, that there is the teacher is consistent, and then the learners must know what convention the teacher is using.
And I think the point you make is that is a convention.
Yes.
Yeah.
It's not something intrinsic to the physics.
Yes, that's right.
It's just a way of remembering, and doesn't actually explain anything.
That's right.
Yes, but what is important is for the teacher to understand the meaning of that explanation.
Yes.
Is there anything that you'd like to add, Kanye?
Yeah, just still on that note to say what we're talking about is the instrument, the tool. But it shouldn't be explained to be more difficult than the content.
Yes,
like
sure.
like Mike is saying, you just know which one you're going to use, and then you take it from there. Because if you spend too much time on it, then learners also try to spend too much time, and then they will miss the problem that they're trying to solve.
Is there anything else that you'd like to comment about?
No, I just thought it was a really nice lesson and very nice use of improvisation in terms of the paper clips.
Yes.
I enjoyed it as well. I think it was a good lesson, and I think that is all what we have for today. Thanks, Liz. Thanks, Mike, and thanks, Kanye. Thanks to the viewers at home. We'll see you next time. Bye-bye.